Welcome to our second lecture on redox chemistry. Previously, we have learned about standard reduction potentials, and we know how to use these standard reduction potentials to calculate the electromotive force of a particular redox reaction. In addition, we have also learned about the Nernst equation, which allows us to study the redox potential independence of the concentration. In addition to these, we will be looking at Latimer and Frost diagrams. These diagrams allow us to look at redox potentials and their relationship in a more schematic manner. In many cases, we encounter species that are derived from the same central element, which exist, however, in different oxidation states. Now, of course, these individual species can be interconverted into each other by redox chemistry, and therefore they are related by standard reduction potentials. Here we can see an example starting from the nitrate anion. In the nitrate anion, the oxidation state of the nitrogen is +5. And you can reduce that species by 1 electron to the nitrogen dioxide species, which involves a standard reduction potential of 0.8 volts. And you can further reduce nitrogen dioxide, again by 1 electron, to the nitrite anion, where the oxidation state of the nitrogen is +3. Now the question is, how can you calculate the standard reduction potential going directly from the nitrate anion to the nitrite anion? So that process involves the reduction by 2 electrons. At first sight, you may suppose that you can simply add these two potentials together to obtain the standard potential for the overall process. However, this cannot be done. On the other hand, it's mentioned here that the free energy, G, is additive, but the potential E0 may not be. So how do you do that? Since the free energies are additive, we can actually look at the free energies of each of these individual processes and then add them together to obtain the free energy of the overall reaction. This approach is demonstrated here. In the first reaction, you can see the reduction of the nitrate anion to the nitrogen dioxide. You can formulate the free Gibbs energy, which is 1 times the Faraday constant times the reduction potential 0.8 volts, and the whole term will be in joules per mole. You can formulate the same for the second step, which means the reduction of the nitrogen dioxide to the nitrite anion, which gives rise to this particular value. Now you can simply add these two together and you end up with this overall value, whereby you simply have the negative Faraday constant multiplied by 1.87 volts. Now this value can be then set into this equation and you will eventually obtain the standard potential for the overall process, which is positive 0.94 volts. So this is one way of doing it. However, you can have a simpler way of doing that, and that brings us to the so-called Latimer diagram, which you can consider a shortcut to calculate such redox potentials. Imagine a process involving a species A, which will be reduced to species B by an n number of electrons, and that process involves a certain potential. And further, B can be reduced by m electrons to species C, again involving a second potential. In order to calculate the overall potential for the complete reaction from A to C, you need to consider the total number of electrons being transferred. And that is obviously the sum of n plus m electrons. Now you can use this simple formula to calculate the redox potential going all the way from A to C. And in order to do so, you simply have to multiply the first redox potential by the number of electrons that it involves, in this case n. And that you add to the second value, which is obtained by multiplying m number of electrons times the potential y. And then this sum you will divide by the total number of electrons, which is n plus m. So the number of electrons involved in the overall process is of great importance. Now, if we apply that shortcut to the aforementioned reaction, which means the reduction from nitrate anion all the way to the nitrite anion, then you have this simple calculation. 1 electron times 0.8 volt for the first potential, plus 1 electron times the second potential, which is 1.07 volts. And that overall is then divided by the total number of electrons being transferred, which is 2. And if you do that, you end up with a same value, which means 0.94 volts, which we have attained by addition of the free Gibbs energy. Now let's look at a more complicated example. Again, we can use our permanganate example. And in this particular case, we are looking at the reduction of permanganate anion to manganese 2+. So this process is something that we are familiar with, but we can separate it into individual processes in which we reduce the permanganate anion with a manganese +7 center by 1 electron to this manganese 6 species. This one can be further reduced by 2 electrons to manganese dioxide, which is then further reduced by 1 electron to manganese 3+, and eventually by 1 more electron to manganese 2+. And the individual standard reduction potentials are listed above the arrow. And the electrons involved are depicted in this case underneath the arrow. So in order to figure out the standard reduction potential from permanganate to manganese 2+, we actually have to add up all these electrons, and if we do so, we end up with a total number of electrons being 5. Of course, we already know that because we are reducing essentially a manganese 7 species to a manganese 2 species, and obviously that would involve 5 electrons. Now, what is also worthy of mention is that all these should happen at pH 0, which means we are still looking at standard conditions because we are looking here at standard reduction potentials, and those are measured at a pH of 0. Now, the standard reduction potential for the reduction of permanganate to manganese 2+ can be then calculated as such: 1 times 0.9 volts plus 2 times 2.10 volt plus 1 times 0.95 volt plus 1 times 1.54 volts, and this will be divided by the total number of 5 electrons. And again, if you do so, you will obtain a value of positive 1.52 volts. And again, you have encountered this value already previously. So to summarize, the Latimer diagram allows you to see the relationship of species in different oxidation states to each other involving the number of electrons and the redox potential. And the Latimer diagram also allows you to calculate specific processes involving these particular redox species. In addition to the Latimer diagram, we will be now looking at the Frost-Ebsworth diagram. Now, a Frost-Ebsworth diagram is a diagram that relates the free energy G of any given redox state to the energy of the element X in the oxidation state 0. The Frost-Ebsworth diagram also tells us the favorable oxidation state of an element in its compounds. In this diagram, the values of N times the redox potential for a particular couple are calculated and then plotted against the oxidation state N. The x-axis of this diagram would depict the oxidation state N, and it must be linear, although some elements do actually not exist in certain oxidation states. Here we can look at a generic Frost-Ebsworth diagram. You can see here the axis, which is labeled with N times the redox potential, and the x-axis is the oxidation number N. And now you can see here, with downwards trend, you can see increasing stability. So this would be the most stable oxidation state of this particular element. So for a given reaction of the element X in a particular oxidation state that gains the number of N electrons to form essentially its element in the oxidation state of 0, the number of electrons transferred, N, is obviously equal to the oxidation state capital N of the species X. So the question is, why are values N multiplied by the redox potential used instead of the free energy values? Now you can ask that question, but actually that's the same thing. The values that are actually plotted are minus delta G, which is the free energy, divided by the Faraday constant. And you know from this particular equation that it is essentially the same thing. Now let us look at a simple example involving oxygen. So oxygen here exists in multiple oxidation states. In this particular case, you have an oxidation state of 0 in dioxygen, and that is related to hydrogen peroxide by a potential of 0.695 volts, which in turn is related to water by a redox potential of 1.763 volts. Now, in this particular case, you have again oxygen in oxidation state 0, oxygen in the oxidation state -1, and oxygen in an oxidation state of -2. And these are reactions that will take place in acidic media, and you have very similar species under basic conditions as well. So here we have dioxygen related to the peroxide anion by this particular value, which in turn is related to the hydroxide anion by this particular value. And you can already see that here we have Latimer diagrams. So the direct relationship of dioxygen to water involves this particular redox potential. And the same applies here, right? So dioxygen is related to the hydroxide anion by this particular potential. Now you have here all the values that you need in order to construct your Frost diagram. So the best way to do that is just to populate this table, and you start with the element in oxidation state 0. That is our dioxygen species. And obviously when the oxidation state is 0, then oxidation state multiplied by the redox potential is also 0, and that gives rise to a total value of 0. Now for the hydrogen peroxide, you have oxidation state of -1 for the oxygen, and the species is the hydrogen peroxide. And N multiplied by E is obviously -1 times 0.695 volts, and that would give rise to a negative 0.695 volts as a value. In basic media, you have the peroxide anion, and you can see that the calculation must obviously be very similar, and so you obtain here a positive value of 0.0649. For the next species in acidic media, those are highlighted in red. We have the water molecule. Oxidation state of oxygen is now -2. And if you know the redox potential all the way from dioxygen to water, which is in this case 1.229, then you can simply take this value and multiply by -2 to obtain -2.458 as a value. If you do not know this value, then you can obtain this value via the Latimer diagram as demonstrated earlier. Now for the last entry, we do a similar approach, and we don't have to go through all this again. Essentially, you get a value of -0.8021 volts. And here you can see the reduction reactions involved depicted again. And what is important to note is that the oxidation state of the oxygen in many of these species are actually negative. So again, we have oxygen -2 in water, and we have oxygen -1 in hydrogen peroxide. Now using these values, we can plot the Frost diagram, and this is already depicted here. So what can we interpret from this particular diagram? The first thing is the lowest point, which means in this diagram it would be this particular species, would depict the species with the lowest free energy, which means that is the most stable species and therefore the least reactive or the unreactive species. And in a particular reaction, this is the final thermodynamic product of the redox reactions involving that particular element. And in this particular case, it is water. So water will be most stable, and luckily it is so because we have a lot of water around, and it is good that it doesn't react further. Next, we consider the lines connecting the higher and lower species. If this connection would give rise to a positive slope, that means the higher lying species is an oxidizing agent. If that would give rise to a negative slope, then the higher lying species is a reducing species. Here, we obviously have a positive slope, so therefore any kind of species above the water or the hydroxide anion are oxidizing. So the peroxide is oxidizing, or the peroxide anion, and has a tendency to be reduced to water. And finally, we look at the species at the top of the diagram. In this particular example, again, this is the peroxide anion. And these species have a strong tendency to convert to those at the bottom of the diagram, because being at the top, it will be the least stable in this particular case. In this slide, we look at the slopes in more detail. So essentially, the slope of the line is the standard reduction potential of the couple. If you look at this analysis, you can essentially calculate the redox potential using this particular equation. And what is more important is you can simply look at the slope, and the steeper the line of the two joining points in the Frost diagram, the higher the standard potential of the corresponding couple. So here we have an example in red, highlighted again the processes occurring in acidic media. And you can see that this slope here is much deeper than this one here, which means the hydrogen peroxide in acidic solution is more oxidizing than the peroxide anion in basic solutions. Similarly, the oxygen is more oxidizing in acidic solution than in basic solution. In this slide, we look in more detail at the species in the convex point. Now you can, for example, connect the hydroxide anion with the oxygen species via this dotted line. And if you do so, you can see that the peroxide anion lies above this dotted line at the convex point. Similarly, the hydrogen peroxide molecule also lies above this dotted line connecting the water molecule and the dioxygen molecule. So these two are the species located on convex points of this particular Frost diagram. And these species, they tend to disproportionate into the individual species, namely water and oxygen, or hydroxide and oxygen. So again, here it is clear that the peroxide tends to disproportionate into either water or hydroxide and the oxygen in both acidic and basic solutions. And here we have a reaction equation depicting the disproportionation of hydrogen peroxide into water and dioxygen. And for this disproportionation, we can calculate the EMF as we have done previously already. So for that, we need to consider these equations. So the hydrogen peroxide gains 2 electrons and 2 protons to form 2 equivalents of water. And you also have this reaction involving the reduction of dioxygen to hydrogen peroxide. And you need to do a subtraction of the second equation from the first one. And if you do that and use these particular values for the redox potentials, then you would come up with this particular value. And again, that is your EMF. It is positive 1.068 volt, which means this is a very favorable process. So delta G is negative, and again, the disproportionation is thermodynamically very favorable and will indeed occur. This slide provides a summary of the information that we can actually extract out of a Frost diagram. Again, the more important information is depicted here. So the slope is reflective of the standard potential. So a higher slope means higher standard potential, and a lower slope means lower standard potential. If you have species above the dotted line, then this one would tend to disproportionate into these two species. And this disproportionation is a favorable process. So you have a process with a negative delta G. In this case, you have a species that lies underneath the dotted line, which means that these two species, this one and this one, would tend to compropportionate to form a species of intermediate oxidation state. And this particular process, again, as you go downhill, means that delta G is negative. Now look at a final example involving a metal ion. And here we look at simple redox reactions involving ion 3, which can be reduced to ion 2, which then is finally reduced to the elemental ion of oxidation state 0. And in this particular case, we are dealing with oxidation states which are always positive. So we have +3, +2, and of course, we always have to relate that to the neutral oxidation state, which is 0. So again, if we apply that and we would populate this particular table, we have always our elemental species of the oxidation state 0. And of course, N multiplied by E would be 0. For ion 2, we have a +2 oxidation state, and that has to be related to the redox potential. So 2 times minus 0.44 volts, that gives rise to minus 0.88 volts. In the last entry, we have the +3 oxidation state of the ion 3 plus ion. And in order to obtain this value, whereby the E0 is not given here, which means the reduction of ion 3 all the way to ion 0, that potential is not given. And so we obtained it from the Latimer diagram, which involves this particular calculation. So if we do that, then we have minus 0.19 volts. And so using these values, we can again draft our Frost diagram. Now this one looks like that. So you have again ion 0 iron 2, and iron 3. Now, if we look at this diagram, we realize that iron 2 is the most stable species because it's the most bottom one in this diagram. And we also realize that this particular spot here is underneath the connecting line between the iron 0 and iron 3, which means iron 2 is a more stable species. And when we have a mixture of iron 0 and iron 3, they like to compropportionate to form the iron 2. And this compropportionation is favorable, as demonstrated by this calculation of the EMF. Again, we will need the first equation, which means the reduction of the iron 3 to iron 2. And subsequently, we need to have the reduction of iron 2 to elemental iron and the respective voltages. And we have to subtract the second equation from the first equation to get the compropportionation reaction, which is depicted here. And if you do that calculation, again, you have a positive value. So that is the EMF. And if you have this positive value, that means that your free Gibbs energy will be negative. And again, this compropportionation will be very favorable. In addition, we also know that if you start from iron 0 and you would like to oxidize this species by an oxidizing reagent, for example, HCl, let's say you treat iron 0 with HCl, then obviously you produce dihydrogen gas and the iron 0 will oxidize to an iron positive species, but this oxidation would then stop at this stage because this one is way below that one of the iron 3. So again, iron 2 will be more stable and the oxidation in the absence of additional oxidant will stop at iron 2. Now this is important note here. Using the reduction potentials and Frost diagrams, we can predict only what can or cannot happen. It will not predict what will happen for reactions between two redox couples. So again, this is like a calculation. You can get a good judgment on potential reactions if you wish. Now this is our last slide for the redox part. And so again, we close this chapter, and in the next lecture, we will talk about the descriptive chemistry of selected main group elements.